Well, good morning, chemistry students. Hey, Monday, April 27th, 2020. Hope you had a good weekend. Today, we're going to add a little bit of vocabulary to what we've been working with. We have something called a polyatomic ion. We have coordinate covalent bonds and resonance structures. So I want you to be familiar with those vocabulary terms, understand what they're talking about. And then we're going to work on drawing some Lewis structures even when the bonding isn't immediately obvious. So what you did last time on Friday, those compounds that I had you practicing, they fit together kind of like puzzle pieces, right? You could see that, oh, this piece wants to make two bonds and these each want to make one bond, so you put them on it. All right, they're not all going to be that simple. So I'm going to give you some techniques when they're not quite that simple. I'm a little bit afraid this might end up being a little bit of a long video, but when I look at, where's the next natural stopping part, I got to get to this. And it's not that there's so much content, but I want to go through a few examples with you, and that's going to take just a bit of time. So follow along, be doing the samples in your notebooks. Certainly, if you get questions along the way, jot a note for yourself that you send it to me so that I can address your questions. So let's start out with that first term, polyatomic ion. And I say a charged group of covalently bonded atoms. And if you think about the vocabulary that you already know or should know, you know that an ion was a charged particle that resulted from gaining or losing electrons. That's still the same. Polyatomic, poly means more than one. So we have a group of atoms. It's kind of like if you had a molecule, which was a neutral group of covalently bonded atoms. If you had a molecule and then you either take one or more electrons or give it one or more extra electrons to make it an ion. Some examples: sulfate. Sulfate is a group of atoms, SO4, so one sulfur and four oxygen, and all together that sulfate has two minuses. That means there's two extra electrons in the structure. Nitrate, NO3, so one nitrogen and three oxygen with one extra electron. Acetate, C2H3O2, two carbons, three hydrogens, two oxygens, one extra electron. I think it'd be a pretty safe guarantee that you have all three of those ions somewhere in your home. Acetate, among other places, in your kitchen cabinets. If you have some vinegar, you have some acetate ions. Nitrates, could be in the garage and maybe a bag of fertilizer, but there's some other places. Sulfates, probably some in your soaps and shampoos and things like that. These ions are around. So let's try to draw a Lewis structure for one of those sulfate ions. And if I take out the pieces, I brought out one sulfur, and I brought out four oxygens, and then two extra electrons. And this is where we start having trouble. If I put that oxygen right on like there, I can make a double bond between the oxygen and sulfur, and that all looks good. But then what happens to the rest of these? This says that they're all bonded to each other. If I just come and put one there, I suppose I could put one on there, and then I could put another one on there, and I could put another one on there, and I guess then I could use my extra electrons to fill it in. It's not what happens. When you see a structure like this with one single atom and multiples around it, chances are very good, and I'll say especially for our beginning exercises here, all four of these oxygen are around that sulfur, and they're all bonded to that sulfur. And to do that just doesn't quite make sense. I mean, I can see where I could bond one here, and I can see where I could bond one down here on those single electrons, but now there's a pair of electrons there. How do I do that? And so we're going to have to change our thinking. Okay? So what I'm going to do, if you look at a structure and it's obvious how the pieces fit together, fine, go ahead and draw it. But if you look at a structure like that last one and it's not obvious how they fit together, I want you to just wipe that whole idea of puzzle pieces out of your head. I'm going to give you a set of steps to follow. Right now, you should pause the video and write these down. I will read through them in case your screen resolution isn't very good and you can't see them. I'll read them for you. Then you can pause each time and write them down. 1. Count the total valence electrons available. That means all the atoms, all the valence electrons. 2. Count the number of electrons needed to give each atom a full octet. So, if I wanted carbon to get an octet and hydrogen or oxygen an octet or nitrogen an octet or chlorine an octet, that's 8 electrons for each. Now, if I were looking at a hydrogen, instead of 8, I'm only looking for 2. That'll make more sense when I do examples. Number 3 says I'm going to subtract these two numbers. I'm going to subtract number 1 from number 2. That's going to give me a number of electrons that I'm going to have to share in order to get these atoms happy. And when we share electrons, we share them in bonds, which are shared pairs. So I'm going to take that number I get from subtracting, I'm going to divide it by 2. That's going to tell me how many bonds I need. Next step, I'm going to guess on the central atom. And I'm giving you 3 criteria. The central atom is very often the least electronegative atom. So if you think about your periodic table, and you know that electronegativity increases up and to the right, take the atom furthest from that corner is a good guess for your central atom. You also would like to look for an atom that looks like it can form multiple bonds. And if I have a formula where there's one atom bonded to multiples of a different atom, the singular atom is usually the central atom. Now, as you look at those, if you can apply 2 out of 3 of those, or 3 out of 3 of those, that's telling you what your central atom is. So once we guess on the central atom and we know how many bonds we have, we're going to try drawing it out. We're going to put our atom in the middle. We're going to put the other atoms around it. We're going to draw in a number of bonds. We might need to put some multiple bonds in. And then we're going to fill in the unshared pairs to hopefully add up to the number of electrons that we use. If we don't get the correct number of electrons that we counted in number 1, we got to look for our mistake. So if you didn't get that written down, pause, write it down before you go on. So let's try to take a look at that sulfate ion with these rules. Step 1 said, let's count up all the valence electrons. All right, here's my count. I've got a sulfur atom with 6 valence electrons. I've got an oxygen atom and another oxygen and another oxygen and another oxygen, all with 6 valence electrons. And then, because of this 2 minus, that structure has 2 extra electrons to use. So I have an extra 2. And when I add that all up, I end up with 32 electrons. Okay? I know this structure has to show me 32 valence electrons. Step 2 says, how many electrons do the atoms want? Well, sulfur would like 8. Oxygen would like 8. The other oxygen wants 8. The third oxygen wants 8. The fourth oxygen wants 8. So altogether, those 5 atoms would like to have 40 electrons. Oh, step 3. Subtract this one from this one. So if I subtract kind of in the reverse order, that means I got to share 8 electrons. Now shared electrons are paired up in a bond, so I divide that by 2. That means I've got to have 4 bonds. Okay, so far I figured out I've got 32 valence electrons altogether, and I have to make 4 bonds. The next step is to guess on our structure. And if you compare oxygen and sulfur, 2 out of 3 of our points point to sulfur being the central. 1, sulfur is further from that corner. It's below oxygen, so it's further from that upper right corner. So it's less electronegative. And there's only 1 sulfur with 4 oxygen. That second point about number of bonds that it looks like doesn't really fit here, because if you just looked at the electron structure of sulfur and of oxygen, they both look like they want to make 2 bonds. That one didn't help us. But 2 out of 3 points say that sulfur is in the middle. So I drew sulfur in the middle, and I put my 4 oxygen around. And we were told that we had 4 bonds. So we just fill in 4 single bonds. Now if we count our electrons that we used, each of those bonds was 2 electrons. So I've used 2, 4, 6, 8 of my original 32 electrons. So how do I finish off? Well, let's try to fill up the octet for everything with unshared pairs. So sulfur right now has 8 electrons around it, no more. This oxygen only has 2 by it, so I'm going to put an unshared pair there, there, and there. That'd be 8 electrons. Okay. Now let's count as we do it. Of the original bonds, we had 2, 4, 6, 8 electrons. This makes 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. It came out perfect. This used 32 electrons by having 4 bonds. Everything's bonded together. We got one more thing we need to do. This structure is not neutral, and we need to indicate the charge. And the charge isn't on any one atom, it's on the whole structure, because we don't know exactly which electrons are which. So what we do for a polyatomic ion is we put the entire Lewis structure in brackets, and we put the charge outside of the brackets. So anytime you have a polyatomic ion, brackets, charge. Let's do another example. So here we've got a carbonate ion. Okay, CO3, 2 minus. Step 1, try to remember, count up all the electrons, all the valence electrons. So carbon has 4, each oxygen has 6, and there's 3 oxygens, and my structure has 2 extra. So 10, 16, 22, 24 electrons. Step 2, try to remember, what is it? Step 2 is count how many electrons all the atoms want, if it could be ideal. Well, we're going to take carbon up to 8 and each oxygen up to 8. That would be 32 electrons. Okay. Step 3, we take the difference between these. So let's see, that's a difference of 8 electrons, which means 4 bonds. Right? 32 minus 24 is 8, divided by 2 is 4 bonds. We're going to guess on the central atom. Carbon is less electronegative. Carbon looks like it wants to make 4 bonds, whereas oxygen only looks like it wants to make 2, so carbon's better there. And carbon is the single atom in that formula, so all 3 of our criteria point towards carbon in the middle. How many oxygen do we have? 3. So I'm just going to put 3 oxygen around. And now I got to make 4 bonds. 1, 2, 3. What do I do with the 4th? I'm going to make a double bond. Now, I don't care if you make the double bond there, or there, or there. Pick one. I'm just going to go with the first one. Now, we'll fill in our unshared pairs. Carbon already has 2, 4, 6, 8 electrons shared. So, no more for carbon. This oxygen has 4 next to it with that double bond. So I'm going to go 6, 8. This oxygen has 2 next to it, so I'm going to go 4, 6, 8. This one has 2 next to it, so 4, 6, 8. Let's go back and count. Hopefully it comes out to 24 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 electrons. Brackets, 2 minus. We just follow our steps. Now, if you had drawn the double bond down here instead of here, that's fine. But then this one would have only had the 2 unshared pairs, and this one would have had 3 unshared pairs. It's okay. We'll get to more on that in just a bit. So here I had it drawn out again. Okay, let's do another example. H3O plus. Step 1. How many valence electrons do we have? Well, hydrogen has 1. Hydrogen has 1. Hydrogen has 1. Oxygen has 6. What does a plus mean? Plus mean it had to have lost a negative charge. It has to be short 1 electron. So I'll just get rid of one of these. That leaves me with 8 electrons. Okay? How many do they want? Well, each hydrogen would like to have 2. Right? Because 2 fills up its valence energy level. And oxygen would like to have 8. So 2, 4, 6, plus 8 is 14. So we have 8 electrons. We'd like 14 to fill everything up. We subtract these 2. 14 minus 8 is 6 electrons. Divide that by 2 is 3 bonds. Okay, just going through the steps. 3 bonds. What's going to be in the middle? Well, hydrogen is definitely less electronegative than oxygen. The thing that wins here, well, there's 2. Oxygen is the singular atom. And oxygen looks like it can form 2 bonds, whereas hydrogen only 1. And here's where we're going to go to extreme. Hydrogen is filling up the first energy level. It's got 1 electron, but it's only got 1 orbital. That's really critical. Hydrogen can never make more than 1 bond. Never. It doesn't have any other orbitals to use to make bonds. It's got 1 orbital that it can share its electron in. So hydrogen is never a central atom. Ever. So I'm going to put oxygen in the middle, and I've got 3 hydrogens. Boom, boom, boom. And this says I'm going to use 3 bonds. Boom, boom, boom. Of my electrons, I've used 2, 4, 6 electrons. Oxygen would like 2 more for 8. The hydrogens are all happy. But this guy is not neutral. It's got a single positive charge. That's called a hydronium ion, by the way. And anytime you have an acid, you got some of these around. Okay? So I know you're watching this probably on Monday. I'm videoing this on Friday. I might go have a fish fry tonight. I might have a little slice of lemon on my fish fry. That lemon has acids in it, and so that acid certainly has some hydronium ions. Chemistry is real. It's around us. Okay, so I had a couple other vocabulary terms. We are getting close to being through this. A coordinate covalent bond. This is a bond in which both electrons are contributed by just 1 atom. Remember, the norm that we've talked about is, this atom's got an electron, and this atom's got an electron, and they both see the other electron, and they both want the other electron, and they come together and they share that pair of electrons. This is more like somebody's kind of leeching on for a free ride. So let's talk through an example. So I'm going to use the example of ammonia Remember, I said to carve that one in your brain? We got NH3. So nitrogen normally has 5 valence electrons. That means it's got a pair and 3 singles. And each of these 3 singles can pair up with a single from hydrogen to make 3 bonds. Okay? There's my Lewis structure for ammonia. If it's obvious how the structure fits together, I don't have to go through all those counting steps. I could. The counting steps will work. Okay? Now let's imagine in our world we have some extra hydrogen ions. So here's a hydrogen ion. It's just a hydrogen atom that's lost its one and only electron, and so it's got a positive charge. And so if you're a hydrogen ion just kind of floating around the universe here, and you look over and say, see this ammonia molecule, and you're like, would you look at that pair of electrons on that nitrogen over there? Now that's attractive. Holy cow! And so that hydrogen is very attracted as a positive charge. It's really attracted to a pair of electrons. So without making any contribution of its own, that hydrogen ion just kind of goes and latches on to that unshared pair from the ammonia molecule. And when all is said and done, we would draw it like this. We have nitrogen with 4 hydrogens bonded to it, and those bonds all look the same now. It's a shared pair of electrons, but we know that somewhere in there, nitrogen contributed both electrons to the bond. That's a coordinate covalent bond, when one atom contributes both electrons. To my knowledge, I don't think we can tell the difference, but maybe out there in the world of chemistry, maybe there is some slight difference from one of these bonds to another, but I don't think so. So let's go back to that atom we had before where we had our sulfur and 4 oxygens and 2 extra electrons making sulfate. And if we looked at the pieces, we have a sulfur, we have an oxygen, another oxygen, another oxygen, and another oxygen, and 2 extra electrons. What if we imagine this guy coming in here? How about if we bring this one over here, flip it over, and bring it in to share a pair of electrons? That looks good. How about if we take an oxygen here, flip it over, bring it up in here, and share a pair of electrons? Okay? Now it kind of looks like the sulfur's full. How do we get another oxygen? Ladies and gentlemen, electrons occupy space in the atom, and we say that there's regions of space with a high probability of finding electrons. Those are called orbitals. But there's nothing that absolutely locks up electrons. Okay? Electrons can move. So let's just, for a mental crutch, think about the electrons moving a little bit. So if I take this guy, and I'm going to ungroup the parts of my diagram, and I'm going to imagine just sliding that electron over, and then I'm going to regroup my diagram. Hey, look, we can have a coordinate covalent bond between the sulfur and that oxygen. I think you can see where we're going. Let's do the same thing with this guy. If we ungroup, move this electron, regroup, bring that atom right down there. Okay? Now sulfur still got its 8 electrons. That oxygen's got 8 by it. That one's got 8 by it. This one's only got 7, so let's use one of these spare electrons from our charge This one's only got 7. Let's use the other spare electron from our charge. And we made a structure where all the atoms are happy using the electrons we had. We had to shift them around a little bit. So rather than thinking about shifting them around, what we're going to think about is those steps I gave you. And we're going to start out by not thinking about the electrons, but think about how many bonds are we going to need, and what should be the shape of this. And then we'll just fill the electrons in rather than worrying about where they came from. Okay? But coordinate covalent bonding is what you can have in the back of your mind saying, yeah, that's how it's possible for some of these things to happen. All right, we're almost there. We're going to look at this nitrate ion, NO3 minus. And if we follow our steps, 1, count valence electrons. Nitrogen is 5, oxygen 6, another oxygen, 1 extra electron. That's going to be 24 electrons altogether. Okay, step 2, how many do they want? 8, 8, 8, 8, 32. And that means that they've got to share 8, which is going to mean 4 bonds. Okay? 4 bonds. Nitrogen is going to go in the middle. Less electronegative, it's a singular atom. And it does look like it wants to make more bonds than oxygen. So all 3 criteria kind of point to nitrogen. But there's only 3 oxygens, so 1, 2, 3. 3 bonds. It says 4, so I got to make a double bond. And then to fill everybody up, I'd have 2 there, 2 there, 2, 2, 2, 2, 2, 2, and a charge. But remember, I could have put the double bond there, or I could have put the double bond there. So the reality is that this structure doesn't perfectly describe it. The reality is it's kind of a blending of all 3 structures. That's hard for our human brains to understand. So here's a picture, and I kind of, these atoms don't like each other, the oxygens don't like each other, so they're going to try to get as far apart from each other as possible. And I drew my structure in 3 different ways. Now to do this next part, I got to go over to my computer for just a second. What I'm going to do is rapidly click between them. And I want you to just kind of let your mind watch it a bit. Now imagine I did that so fast that it just started to blur these images together. And effectively what you saw is 1 1/3 bonds there, and 1 1/3 bonds there, and 1 1/3 bonds there. How can you have 1/3 of a bond? Remember, what's really happening here is we have regions of space that are likely to hold electrons. Okay, there's a high probability. And so what we're saying is that 2 of the electrons in this are less localized and are really kind of shared around. That's getting to a little bit more advanced topic, but we're not going to take it much further than that. I just want you to know that there are structures that have more than 1. Now, if I don't specify, I will accept from you if you just draw me any one of those. But if I ask you the question, when we have a situation where one structure by itself doesn't entirely describe the structure, the molecule or ion, what is this called? These are called resonance structures. These are structural formulas used when one structure by itself cannot adequately describe a molecule. So that nitrate ion has 3 equivalent resonance structures. And the best description of a nitrate ion would be a blending of those three structures, not any one by itself. Resonance structures. Sure, we can do this one more yet. Here is sulfur trioxide. Notice there's no charge on this. So if I count my electrons, 6 from sulfur, 6 from each oxygen, is 24 electrons. Each atom wants to fill up its octet with 8. 32 electrons means we got to share 8. It's going to be 4 bonds. Sulfur in the middle, oxygen, oxygen, oxygen. 1, 2, 3, 4 bonds. I got to choose one. Okay. The reality is, it could have been, I could have drawn a double bond there, or could have drawn a double bond there. So there's 3 equivalent structures that we could get, and that's really what I'm after here. Again, showing you. In this case, we're going to end up with 3 different resonance structures for sulfur trioxide. All right. So again, that may have gone a little bit long here today, but that should help you do. I'm going to give you another worksheet with some of these to practice. And I think I said already in the last video, as we go through questions for the rest of the chapter, very often the place we start is looking at a Lewis structure to answer all sorts of questions. So you want to really get good at drawing Lewis structures. Practice. If you have questions, let me know. Take care. Have a good day.